Thank you very much. I'm Laurette Dubé from Des Hôtels. I'm an emerita professor in marketing, mind you, but most critically for this, I am the founding chair and scientific director of the McGill Center for the Convergence of Health and Economics. And from the center has been created 2013, so more than 10 years ago. And when we talk about what AI can do and cannot do, it can be very catalyst to get real about this convergence between what we can afford financially, logistically, and so on, and the way we can create value for everyone. And from an AI perspective, Giancarlo Stark, as you can see, it's about trustworthy system, but trustworthy system need to be trusted by everyone. And that's essentially what we will be elaborating together in the 2 hours that we have. So without further blah blah, I'm very pleased to welcome Giancarlo Guisardi. Giancarlo is a friend and colleague working on many aspects of food and health with me. He is one of the, I would say, one of the most interesting combination of scientific rigor, creativity, and wrapping this in an intent to make the world a better place. So Giancarlo is full professor of software science and evolution, as well as chair and department head of Semantic, cybersecurity and service at the University of Twente in the Netherlands. I won't read the long bio that you have there, all of it, but what is important in the context of acting in the real world is a main contributor to the upcoming ISO IEC International standard for unified foundational ontology and to OntoUML modeling language that is very central to a lot of the integration of data and so on. Giancarlo, welcome.
Thank you very much, Laurette, for the very nice presentation. Thank you all for being here, also the people online. It's a pleasure and an honor. I told Laurette that Canada has a soft spot in my heart because it's the first country I visited when I was a kid. So the first time I went abroad was to Canada, including to Montreal, and it's the first time I'm coming back. So I'm very happy to be here. So this is going to be a talk about semantics, ontologies, as Laurette said, about trust in a very particular sense. I actually did a lot of work on trust and on ontologies of trust, on trying to understand what trust is about. But this is going to be about trustworthy systems, and in particular, the role of trustworthy models in building trustworthy systems. And it's going to be more about intelligence, more about IA than AI. So more about intelligence augmentation. So how can we use a computational process to amplify, to augment human intelligence? So I'll start with, let's say, so how do I go about it? Yes, with some observations, which I don't think are controversial at all. The first one is that any software system embeds a representation of reality according to a particular worldview, right? So any system, in fact, any information artifact, so even if we take, this is the subway of Amsterdam, this thing, it has meaning because we can map symbols here into a kind of theory of the real world, right? So this thing makes an ontological commitment to a world in which there are things like lines composed of stations, which are ordered in a certain way, that have a certain direction, that can intersect, and so on. So this is basically a data set, a set of propositions, and this thing makes a commitment to a world in which these things exist, having these properties and being constrained by certain rules. And this is, of course, true also for any information system. So the most mundane of database, this one here, for example, about transplants, believe, quote unquote, in the existence of people who can believe in or deceased, about transplants, and that transplants involve surgeons, donors, donees, and so on. This is a very old idea in computer science. In fact, this is a very nice paper from 1967 by a guy called George Milley. George Milley is a big deal in computer science. He invented something called Milley automata. He was also the PhD supervisor of a guy called Peter Chain, who invented entity relationship diagrams. So he's like the grandfather of conceptual modeling. And in this paper, Milley makes this point that, you know, data are fragments of a theory of the real world, and that data processing is basically manipulating this theory. It's about manipulating this theory. And that this is an issue of ontology, or the question of what exists. So this is the first mention of the word ontology in computer science in 1967. So Milley's point that I'm amplifying here is that the point is actually this one, that we can't escape this, that the opposite of ontology, so the sentence is mind, but that's the spirit of what he was trying to say, that the opposite of ontology is not non-ontology, it's bad ontology. You are doing this anyway. So every time you have any program that has what is called real-world semantics, which is not just a piece of mathematics, this thing is making an ontological commitment, right? So if you have a Python program that has variables like patient and hospital and treatment, this thing is committing to a theory of the real world. So an ontology with a lowercase o is a theory about what kinds of entities and their ties are assumed to exist by a given description of reality. And this is absolutely unavoidable. Second point, modern software systems are kind of built in a collective and a distributed manner, right? So there is almost no greenfield development anymore. You build information systems to connect them to other information systems, or by connecting existing information systems. So even if you look at, you know, the 4 V's of big data, the tough challenges are actually here. I mean, on dealing with variety, and also including semantic variety, and with veracity, because veracity is also about the relation between the representation and the world, the part of the world which is represented there. So if we have to deal with variety, because basically all interesting questions we need to have answered in science, in government, in organizations, can only be answered if we put together data that now reside in concurrently developed data silos. So you have data spread out everywhere. All the interesting questions we need to have answered can only be answered if we put this piece of data, this datum together. And each database makes a commitment to a given ontology in the definition I just mentioned. Connecting this data is it boils down to connecting these ontologies, to finding out the relation between the reference of this data in these different theories. And this is exactly the problem of semantic interoperability, relating the different worldviews expressed in these different representations, or relating these different ontologies. It's finding out, for example, how person here on the left relates to person on the right, or how transplant on the left relates to transplant on the right. Can we assume this should be a relation of identity just because we are using the same lexical term? If not one of identity, what are the options? So what kind of relations can we have there? Maybe one of specialization, parthood, maybe a type of dependence. Then what kind of dependence? Generic dependence, specific dependence. Maybe it's causality, maybe it's manifestation, maybe it's historical dependence. There could be many options. So what do we need to do to address this interoperability problem is, one, find out what are the theories embedded in these different systems, find out how they relate to each other, and find out what that entails. Once I have a particular type of relation, what would that mean? What does it mean, for example, to be identical to something else, right? What is the semantics of identity? So identity is an equivalence relation, right? Everything is identical to itself. If A is identical to B, B is identical to A. A is identical to B and B is identical to C, A is identical to C. Identity also follows what is called Leibniz law. So if two things are identical, they necessarily, in every possible world, have the same property. So it's a very strong relation. So we better be sure that we are talking about identity. And then again, if something else, if dependence, what kind of dependence and what does that mean? So in order to solve this problem, we need the help of a toolbox, of a conceptual toolbox. And that's exactly what ontology, capital O, means. Ontology is an area devoted to developing this domain-independent toolbox with tools for ontological analysis. So more than an artifact, and I think the real contribution of ontology for computer science, and to this problem in particular is actually the method of analysis, not the artifacts. Third observation, in critical domains, we need these ontologies, these artifacts, these reference conceptual models, domain models that represent the theories embedded in the systems to really serve as meaning contracts. These are not about data, not primarily about data structuring. It's really about representing a theory of the domain that tells the world what your worldview is. And the problem there is a problem of validation more than anything, right? So it's not just a problem of guaranteeing that your model is consistent, for example, it's a problem of verification. It's really a problem of finding out if your model really represents the conceptualization you have of that domain. And this could be seen as a problem of finding the relation between these two sets. So imagine if you have set A is the set of possible interpretations of a given model, and the set B is the set of intended interpretations of a given model. If your model is too loose, what happens under constraint is that it would accept as possible interpretations many interpretations which are not intended. If it's too rigid, too strict, it will exclude intended interpretations from being valid. So the real problem of coming up with an ontology or a conceptual model as a contract is finding out the exact set of constraints that will make these two sets coincide, meet. Because if we don't, we can have two systems. We don't have access to the conceptualizations, just to the artifacts. And we could have here what is called a false agreement. When we think we are talking about the same thing, when you think system A has an idea of patient, system B has another idea of patient, we think they have the same idea of patient, but they coincide on the possible interpretations, but not in the intended ones, right? So it's not a problem if we disagree, but it's a problem if we falsely believe we agree. And here is the fourth problem, that exactly in critical domains like cybersecurity, like finance, like healthcare, in which we need these models to be airtight, these models are extremely complex. So this is what a friend of mine calls a ridiculous gram. This is a real model, or this, right? So how do we understand these things? How can we understand if this model expresses exactly the set of intended interpretations if we cannot even understand the model? So ontology is becoming more and more salient as a possible solution for these problems, which are all related to trustworthiness. I'll come back to this. So this is, for example, Microsoft now talking about this idea of fabric IQ, which is the idea of a semantic fabric of the organization, or what they call the operating system of the organization. This is CIO magazine basically talking about the same thing, that we need shared meaning. AI can only work under a constrained environment in which you have this shared meaning and well-structured semantic relations. And of course, the Palantir's ontology, right? So the fastest growing company in the world that explicitly says its secret sauce is its ontology. So what kind of ontologies? The focus I want to give in the second half of the presentation is this idea that we can only, because of the observations, because of the premises that I just mentioned, we can only have trustworthy models, systems, if the systems rely on trustworthy models, right? And trustworthy models are models that are reliable, both so sound, both from a formal and an ontological perspective. I'll illustrate that. They are domain appropriate, so they really represent, they are truthful to the domain they are representing. They are resilient, so when you change the model, you don't have ripple effects. They are explainable. I'll talk a lot about explainability tomorrow, but here with a very narrow focus on semantic precision and semantic transparency and cognitive tractability. They are reusable across applications and implementations, interoperable and evolvable. Here is a commentator, John Bittner, in this commenting on Michael Burry, the guy from the Big Short, shorting Palantir, and commenting on this that the fact that Burry wasn't shorting the idea of ontology, but the execution. Why Palantir's ontology is not a good example of ontology. And he's making a good case here that ontology should be done right using, as I said before, this toolbox in the construction of these artifacts. So they should be grounded in top-level ontologies like BFO and like UFO. So I'll talk about UFO today. So that this is necessary so that we can have machines that can reason, can check for consistency, and can explain their decision-making process. UFO is coming up as an ISO standard. Is this top-level ontology? It's one of these toolboxes with very general theories about events, causality, dependence, parthood, and so on. And what we did was, and this is something kind of unique for this foundation ontology, is that we actually have we have a language that would shield the user from having to deal with the foundation ontology directly. So we embedded the ontology in a language system. And this language is a conceptual modeling language. It's a diagrammatic language. It's a pattern language. So the actual modeling primitives of the language are a number of design patterns. It's associated to a methodology for producing interoperable and explainable models. It has an entire tool ecosystem for model building, pattern-based model construction, for verification, for validation, for verbalization, and for a bunch of things. I'll mention, let's see how much time I have to mention some of these tools. It's being adopted in a number of domains now for more than 2 decades, and it's also in the road to standardization at the OMG. So what I'll do now is to show how this language can be used to address some of these requirements for trustworthiness with respect to models, by giving you a primer on the language. So OntoUML is a diagrammatic language. It's an extension of UML, of the Unified Modeling Language. But instead of having just these general notions of types, it makes finer grained distinctions among types of types. So it distinguishes, for example, between a kind, so a type that classifies entities necessarily, that describes essential properties of entities in that domain. For example, here we have 2 kinds of things, people and organizations. We are, for example, necessarily a person, but we are only contingently a healthy person. So I could become a sick person, I could come back to becoming a healthy person, and this will have no effect in my identity. Then we have types that are both contingent and relational, like being a patient is being, in this example, an unhealthy person, but that's treated by a healthcare provider. And being an individual healthcare provider is also a person that provides healthcare treatment. So both relational and dynamic. And then we have types that classify things of multiple kinds. Like, for example, being a healthcare provider here classifies both entities of the kind person and of the kind organization. And this solves, by the way, a very common modeling problem, which is this one. So if you want to say, for example, that customers can be both people and organization, if you do this, you run into a logical contradiction. The solution is actually recognize that customer is not, it's one of these dispersive types that crosses the boundaries of different kinds. So customer could be specialized in personal and corporate customers, which are of the kind person and organization respectively. And here you have a pattern. So if I could offer you a geometric metaphor, it's like your world is tessellated into kinds. Everything belongs to one kind, one unique kind, and they cannot move in and out of those kinds. For example, person, car, organization. Roles and phases, so roles like being a patient or phases like being a sick person, are shadows that move in the space of kinds without ever crossing the boundaries of kinds. So for example, being a student or being an extinct organization, an active or extinct organization. We have these things called mixins, which are the things that cross the boundaries of kinds, right? So we can have mixins which are static, like being a physical object. We can have mixins which are dynamic, like being a customer or being a healthcare provider. So here we have in the background a kind of tiny ontology of types, right? We have what are called sortals, which are either kinds or specializations thereof. And we have these mixins, which are the things that cross the boundaries of kinds. All the examples I used so far are examples of objects, so things which can exist independently. But then we can have things that can only exist if other things exist. Like, for example, a symptom that is existentially dependent here on an unhealthy person. Or a treatment that can only exist if both the patient and the healthcare provider exist. And these objects, so these distinctions that I mentioned up to now, they can be used now to qualify, to specialize these types of dependent things. So a treatment, for example, can be specialized in inpatient and outpatient treatment, a static classification. They can be decomposed into, so a treatment here is a bundle of legal positions, rights, obligations, liabilities, powers. They can go through phases. They could be active or suspended. They could be an insured treatment, which is a role played by the treatment itself. So all those distinctions can be applied also to these independent objects. We also have here types whose instances are types. So for example, the type healthcare profession, the instances are not individuals, but they are the subtypes of individual healthcare provider. So it's the type physician and the type nurse that are instances of the type healthcare profession. So what does this thing buy us, right? Here's the first one. We can now be very precise on how we model the general terms in our domain. So these things, being a person, a man, an adult man, a living person, they are not just logical predicates. They are not just classes, right? So for example, Mick Jagger here instantiate all these types, but not in the same way. So what's going on here is those meta properties that I use to create distinctions among types of types, static versus dynamic, relational versus non-relational. Now I can use as methodological guidelines for deciding how to model things in my domain, my universe of discourse here, right? So I know that person is a kind in this domain because it provides a uniform principle of identity for all its instances and describes its essential properties. I know that being a singer or an economist or a British citizen or a knight of the British Empire, these are all roles played by Mick Jagger because it's dynamic and relational. They're all played by person as well, not crossing the boundaries of kinds. I know that being a living person or an adult man, these are phases because they are dynamic and non-relational. And I know that there are types like being a physical entity or a cultural heritage item that Mick Jagger shares with the Taj Mahal, for example, right? So here, these properties, actually, the conjunction of constraints associated to a type, like what it means to be a role, actually, they can become grammatical constraints in this language, right? So they come from the axiomatization of the ontology, a micro theory of what roles are, and they become grammatical constraints in the language. So we have here, for example, roles are such that all instances of a role are of the same kind. For example, all patients are people. All instances of a role instantiate that type only contingently. For example, no patient is necessarily a patient or a student. Instance of a kind instantiate that role when participate in a relational context. People are patients when they have a relation to a healthcare provider. And also things like roles cannot be a supertype of a kind because you run into a logical contradiction. So in the grammar, you cannot build models like this. These models become grammatically incorrect. They won't compile but in a tool. And then you can actually build a tool that checks for this, does verification and checks for all these mistakes, guaranteeing this type of ontological consistency in the model. But you can actually do better. Because what's going on is, because this notion of role is now constrained by all those rules, by all those constraints, you can only model roles in a model, in an OntoUML model, following a very constrained structure. So we have a design pattern that emerges there. Every time you have a role, it will eventually specialize a kind. It will be defined in a relational context, having the right types of cardinality constraints. So here is an example of an instance of that pattern in this model. This is another pattern related to phase. So if you are a phase, you can always move out of that phase, but you cannot move out of the kind. So you have to move into another phase of the same kind. This is a pattern related to these relational conditions like treatments, or here the regulatory decree that defines a healthcare profession. Here is a higher order type pattern. So the entire model is a collection of patterns. So you build the model by instantiating these patterns, and we actually read the model by looking and finding these patterns. So this has interesting cognitive consequence. Talking about cognitive tractability, another thing you can do, as I showed you before, these models can get very complex. This is, something that people in computer science and conceptual modeling, data modeling, that have been trying to address for years, which is how do I, for example, modularize a model with 15,000 classes, for example, right? How do you automatically do that? Or how do you abstract? So imagine you have this problem, like you have a model with 5,000 classes, generate a summary of this model, kind of that really captures the gist of what the model is about, but with 500 classes instead of 5,000. How do you do this in a language that is completely neutral, right, from an ontological point of view, like ER diagrams or OWL or UML or logics, because everything is the same, right? All types are in the same logical footing, and so are all relations. So here, you can actually leverage the ontological semantics of the language to do this. So modularization, for example, we look at these relators, these relational objects, which are existentially dependent on multiple objects, like, treatments, enrollments, employments, presidential mandates, marriages, the bread and butter of information systems, right? And insurances and so on. So we look at these things, and we have an algorithm for breaking down this model following this relational context. So you take a model like this, and you produce something like this. It breaks the model down in contexts, frames like car rental, the employment, the car ownership, the marriage, and so on. And it does that automatically, regardless of the content of the model, and in a way that's very computationally efficient. Another thing that we do, leveraging the semantics of the language, is this kind of abstraction. So you can take this model and you abstract the model to the kinds, right? And you have a very simplified view of the model, again, in an automatic way, in a way that is independent of content and computationally very efficient. Another thing you can do is, from this conceptual model, generate a number of different artifacts that would codify this model, right? So we separate the problem of conceptual modeling when building ontologies from the problem of implementing these ontologies in computationally efficient language. So what do you want to do when you are doing conceptual modeling to address this problem of semantic interoperability? Is to build a model that is very expressive, very precise, truthful to the domain you're representing, and that would help people in tasks of domain understanding, problem solving, meaning negotiation. Once you have that, then you can generate partial versions of this model addressing different types of non-functional requirements. So one example is this language called OWL, the Web Ontology language, that you can use for doing reasoning, for doing efficient reasoning in a particular context. What we have is it's basically a compiler that will generate our code automatically from this OntoUML models. But it also generates code in relational database, in programming languages, in labeled property graphs, in anything we want. Interoperability. So this language will help you find out if the things you have, which have the same name in different models. How much time do I have? 5 minutes. Yeah, I think I can do it. If they are or not the same, right? So here we can immediately see that person on the left cannot be identical to person on the right, because person on the right is a face and person on the left is a kind. So actually, person on the left is identical to human being on the right. Also, the transplant here on the left is this bundle of commitments and claims and so on, so a kind of contract between individuals. And transplant on the right is a type of events, so the type of transplants that can be performed by someone with a particular license. Even very simple concepts like the concept of, I mentioned patient, but let's go even simpler, the concept of person. What do we mean by person? Do we mean a human being, a legally recognized human being, a cognitively capable human being, so someone who can be responsible for their acts, or legal person in the sense of legal party that would include organizations. So this would be mapped to very different ontological types. So here, imagine you have 4 models with one concept, and how we can put them together is already not trivial. Again, the problem of interoperability, of semantic interoperability, is guaranteeing that you have this model here with its possible interpretations and intended interpretations, that when you plug in another model, that the intended interpretations are preserved, right? And this is very hard, because finding out if this model here already is constrained enough to exclude all non-intended interpretations is very hard. Remember, what we're trying to do is to find out the right set of constraints here to do that, right? Some of these constraints come for free in a language like OntoUML. Why? Remember, these patterns are basically representations of micro-theories. So when I use a pattern like this, I'm doing a theory inclusion mechanism. Don't bother with the formal language saying every patient is a healthy person. Sorry, it's an unhealthy person. Every patient can cease to be a patient. People are patients when treated by healthcare providers and so on. So this axiomatization is coming for free because you instantiate that pattern. However, there are things that a general language system cannot know about domain-specific rules. So what we have in this language is a way to simulate the model. So basically generate the possible interpretations of the model. So if we take a model like this and we do that, we're going to see possible instance. So this is a synthetic instance of that model, right? Saying, here's a transplant with 1 donor, 1 donee, and 3 surgeons. But as you iterate through the set of possible instances, this is going to pop up. You donating an organ to yourself and performing the transplant, which I guess is possible, but not a very good idea. Then the first, when people see this and they try to rectify the model, what they do is to declare these 3 roles as mutually disjoint, right? But then when you run the simulation again, what you get is this, someone who donates an organ could never receive an organ, and someone who's a surgeon can never be a donor or a donee. So you are over-constraining the model. So you play the simulation game until you are convinced that you got the right model. Actually, what we identify by doing the simulations in an entire data set of models is that so patterns starting to emerge, anti-patterns. So fragments that when present in the model will create this dissociation between the set of possible and intended and unintended interpretations. So every time you have this relational context connecting roles, and these roles take their identity from the same kind, of course, it can be the same instance playing more than one role. In fact, there is an instance of that in this model. Can you see it? That this model has an instance of this anti-pattern. It's here, right? So because a healthcare provider can be both an individual healthcare provider who's a person and a corporate healthcare provider that is an organization. A possible instance of this model is one in which the healthcare provider and the patient are the same entity. Last thing I'll say, evolvability. So how do we go about evolving these models? Imagine you are simulating this thing and generating all these possible interpretations. So, and users are validating their models by looking at the interpretations and seeing, I want that, I don't want that. What we can do is to, so what they are doing is actually curating a database of examples and counterexamples. So we can use a very old and very efficient machine learning algorithm to roll back the clock, inductive logic programming. So we have a background theory, we have a database of examples and counterexamples. So even with a small data set, we can learn the missing constraints. So for example, imagine you have this, people can believe you are deceased. And so this, in logics, it would be something like this. And you generate all these possible interpretations, and people look at that and they mark which ones are intended and which ones are non-intended, not intended. And then what the algorithm will do, will try to abstract these patterns, right? And say, you cannot have a person who's neither living or deceased, and you cannot have a person who's both. So just my last set of slides. I think this is the takeaway message, which is beautifully expressed in this paper from 1985 by Brian Cantwell Smith, one of the great philosophers in computer science, unfortunately, who passed last year, actually. So he's writing in 85 in a conference about the Cold War and so on, about software correctness, right? And he expresses in a really nice way. He says, I have chosen to look at modeling in this paper because it exerts the most profound and most important influence in the systems we build. To build a model is to conceive the world in a certain delimited way. It is with respect to these representations that computer systems work. They run by manipulating these representations. This can all be summarized in one slogan: no computation without representation. Mediating between the system and the world is the inevitable model. What we have been focusing on as a discipline is the study of the relationship between the model and the system. What about the relationship between the model and the world? Any adequate theory of system correctness or trustworthiness will have to take the model-world relationship into account. That's it. Thank you.
Am I allowed to ask a question?
Well, you're allowed everything.
Please ask questions. If you want to ask a question, make sure you turn on the
microphone. This is very interesting, these concepts of trustworthiness. And when two sub-questions in some way. When I was making my introduction comment, I was talking of systems that are trustworthy and systems that are trusted. Yes. Can you comment on this?
Yes.
How to make sure that there's not too much of a gap if you want the various agents in your system to act upon?
So in a nutshell, I think the distinction is an ontological versus epistemological one. So I think to be worth of trust is a property of the system itself. To be trusted is about the beliefs of agents, right? How agents believe the system. So trust is basically a set of beliefs of a truster about certain properties of the trustee. Basically, the capacity and intention, if it is the trustee is an agent, the capacity and intention of the trustee to behave in a way that's favorable to the truster goals. So it's about beliefs, right? It's an epistemic notion. We need really systems that are worth of trust.
No, thank you.
We need systems to be trusted as well, but it shouldn't be unwarranted, right?
Thank you.
Yeah. So Giancarlo, yeah, wonderful. And
thank you.
It looks awfully like the HL7 array model and the examples you give. So is this work and with leveraging some of the array model?
No, really. I was just coming up with examples, you know, because I thought it would be,
Oh,
yeah,
okay.
it would speak to you. But we have been using the language in so many different domains, in many different domains, in space, in finance, and
I see.
we are actually working now with people from NASA to build a plugin based on this
I
language.
see.
So it's I perhaps it's
It's
fly there.
so similar. Yeah.
We've done a lot in healthcare as well. For example,
Yeah.
in the Netherlands, so there is one organization in the Netherlands that organizes, that integrates all the different healthcare systems in the Netherlands, and they adopt this as a kind of de facto standard.
I see.
As a language.
Yeah. But last question.
Yes.
So it's very nice you say that this ontology, right? So it's some kind of commitment and between the
Yes.
representation and what you see. So in the traditional way, like a UMLS, and it's lots of manpower goes in, right? Thousands of man years and goes in to actually get those concepts and the relations. So now in the era of big data and the AI, is there any new way of generating ontology?
Yes, that's a very interesting question. We are actually working on that because it turns out that these LLMs know a lot about this language.
Yes, of course.
Right.
Yeah.
So what we did, and because they work so well with textual language, we have a version of OntoUML. It's a textual syntax called Onto, textual Onto, and we've been trying to interact with that and to see to which extent the language, the systems can partially generate the models. We've been feeding existing models in the context. We've been feeding the actual grammar of the language to an LLM, and the results are starting to look interesting. I think we are still a long way to go. I really don't believe in a type of vibe modeling scenario, but I think we can automate the part of the, or at least not anytime soon, but I think we can automate a large part of this process. And again, I think if we have a foundation ontology, plus this set of ontology patterns, plus some existing ontologies which are very, so let me roll back and answer this question a different way, right? So ontologies can exist in different levels of abstraction and generality. So here at the top, we have this foundational ontologies, which can be used in any different domains. Then we have ontologies for specific areas, but which will cross-cut several different domains, like trust, for example, right? Or risk or value, the discussion we were having. And then we can extend those things to domain ontologies, talking about software trust or financial risk, right? Or infrastructural risk and so on. I believe that LLMs could play an important role in speeding up the process of building the domain ontologies. And I believe having good foundation ontologies and good core ontologies will really help with this process, right? They can provide context for the generation of the domain ontologies. So yesterday we had a very interesting exercise on services, right? It's very important that we are able to recognize that the type of phenomenon we are modeling can be mapped to one of these mid-level and top-level infrastructures. In the same way, I think we can teach machines to recognize that. It's in a sense an exercise in abstraction to say what we're talking about here in patient care, this is really about services, about service offerings, service agreements, service deliveries, and so on. And by the way, so is a music festival. So when you're talking about a music festival, you're talking basically about three things. You're talking about services, right? Service offering, a service agreement, which is your tickets, right? You're talking about events, which happen in space and time, have certain temporal ordering between them, participants, and so on. And we're talking about artistic expression, so genres and copyrights and stuff like this. That's the way I think we can build better ontologies, better, both humans and machines. Thank you.